So hello everyone, I'm Norman Wahlberger, and today in this short course on probability and statistics, we're going to talk about things called probability spaces, the idea of an event, and conditional probabilities. So what we're doing now is we're trying to take that rather informal approach to probabilities that we were talking about last time and formalize it a little bit by introducing some mathematical structures that will cover a wide variety of situations. Okay, so the first definition is that of a sample space. All right, so what's a sample space? It's the set of possible outcomes to an experiment. And the experiment is rather general. It could be a mathematical experiment, or it could be a sociological experiment or a physical experiment, rather general situation. So for example, if we throw a dice, then the sample space is we'll usually denote it by S. So it's a set, all possible outcomes, 1, 2, 3, 4, 5, 6. In this case, each of the outcomes is equally likely. Each outcome is equally likely. But that doesn't have to be the case, but it is in this case. In fact, the probability of each one is 1/6. So the probability of any one outcome is 1/6. Okay, if we roll 2 dice, and count the sum, the total, then the sample space is, well, in this case, the smallest total that you can get is, of course, 2. And then you can get any total up to 12. So the sample space, in this case, is the set 2, 3, all the way up to 12. And, of course, in this case, the outcomes are not equally likely. And the experiments don't really have to be real experiments. They could also be perhaps a thought experiment. For example, a horse race with 3 horses, let's say Black Caviar, on, let's say, Kingston Town, another famous Australian horse, and Phar Lap. Okay, so these horses are no longer around, but we still could imagine a horse race like this, and we could kind of talk about the relative probabilities of them winning. So in this case, there would be essentially 3 possible outcomes if we're only interested in the winner. So the 3 outcomes would be Black Caviar, or Kingston Town, or Phar Lap. And the probabilities in this case are highly dependent on your perception of the relative aspects of the horses. So the probabilities are matters of opinion. Well, not just opinion, but also knowledge, familiarity with the horses and their trainers and so on. Okay, sometimes it's nice to visualize a sample space. So we can do that with this kind of example. So let's just have a situation where we represent the possible outcomes by the little squares in a chessboard, say. So I'll divide this into 64 squares. Okay, so there we have 64 little squares, each representing a possible outcome. Okay, and one more example that we'll have a look at later is the example of a lottery. All right, so we'll suppose that there's a lottery where we have 10 million tickets. Each costing $1. Okay, and there is a couple of prizes. So there's a grand prize. G is the grand prize. And let's say that's $1 million. And then there are 10 second prizes. Let's denote them by S, of each worth, each giving you 100,000. And then there's 1,000 third prizes. We'll denote them by T, each giving you $1,000. And then there's 1 million consolation prizes. And we'll call them C. And the consolation prizes are a free lottery ticket for the next draw. Okay, so what are the possible outcomes? In this case, the sample space, the experiment is the lottery, and the possible outcomes are, well, you might be lucky and get the grand prize, or you can get one of the second prizes, or maybe a third prize, or a consolation, or I guess there's a fourth or fifth possibility, which is probably the most likely one, that you get nothing. Okay, so N represents no prize. And of course, the relative probabilities of these are vastly different. This is a very low probability event. This is a reasonably high probability event. All right, so that's the general idea of a sample space. Now let's talk about probabilities on these things. So the definition is that a probability measure, and we'll denote it P, a probability measure P on a sample space S of the kind that we've just been talking about, is a rule that assigns to each outcome S in capital S a probability. And we'll call that probability little p of S. Well, that's got to be bigger than or equal to 0 because it's a probability. And we have to have this rule has to satisfy that the total probability, the sum over all S of little p of S, equals 1. So the total probability has to be 1. All right, so in most of the examples that I gave you about sample spaces, there's actually natural probability measures associated to them. So let's have a look at the space where you roll 2 dice and observe the total. All right, so here the outcomes, I remind you, were 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12. And the associated probabilities are, so These are well known to people who play things like backgammon or games involving dice. So the probability of getting a 2, if you roll 2 dice, is 1 over 36, because there's only one way of getting that, is to roll a 1 and a 1. The probability of that is 1/6. The probability of a 3 is 2/36. The probability of a 4 is 3/36, and then 4/36, and then 5/36, and then 6/36. That's the maximum for a 7. And then after that, it sort of declines symmetrically. So 5/36, 4/36, 3/36, 2/36, and back down to 1/36 for 12. And you can verify that those numbers add up to 1. Right? So getting a 7, for example, is exactly 3 times as likely as getting a 3. For example, in craps, that's why 7 plays a critical role, because it's right at the maximum if you're playing craps. Okay, another example might be, for example, in our horse race. So some expert bookie might judge that the various probabilities of the various horses might be, probability of Black Caviar winning might be 1/2. And the probability of, say, Kingston Town winning might be 1/3. And the probability of Phar Lap, that would have to be then 1/6. That might be one bookie's estimate of the probabilities if there was such a possible race between the 3 horses. All right, so when we have a sample space together with a probability measure, well, then we call that a probability space. So a probability space is a pair, is a sample space S with a particular probability measure on it. P. And we might write that combination just by writing the bracket S and P, representing the set together with the probability measure. All right, that's a probability space. And that's, in some kind of sense, the natural framework for doing a lot of probability. All right, so let's have a look at now the notion of an event. So events. An event, usually denoted E, is a subset of a sample space, S. Just a subset. So E is just a subset of a sample space S. If S is part of a probability space, which we'll assume, if SP is a probability space, then we define the probability of the event the probability of the event E is P of E, and that's just the sum of all the probabilities of the various constituents of E. So it's the sum of all the S belonging to E of the probability P of S. So for example, suppose that we roll a single dice And let's suppose we're interested in the event of getting an odd number. So let's let E be the event. Get an odd number. So we say that in words, let E is the event of getting an odd number, but mathematically we're just talking about a subset of a probability space. So here the S is the set 1, 2, 3, 4, 5, 6. That's the set of all possible outcomes. And the set E is the set 1, 3, 5. And so the probability of E is the probability of getting a 1 plus the probability of getting a 3 plus the probability of getting a 5. So that's 1/6 plus 1/6 plus 1/6, which is a half. As another example, suppose we roll 2 dice. So that's a different sample space, different probabilities. Now let's consider the event. Let E be the event. Get an odd total. Or maybe an even total for something different. Get an even total. All right, so what's that? Well, then E, the probability of E, of the various totals, we're talking about the probability of getting a 2, or 4, or 6, or 8, or 10, or 12. So our sample space is now this set 2 up to 12. With the probability distribution that I talked about there. And so this probability will be, P of 2 we said was 1/36, and then we add 3/36, and then 5/36, and then another 5/36, and then a 3/36, and then a 1/36, for a total of how many 36? 10 in the middle, plus 6, plus 1, so that's 18/36 for a total, which is a half. Maybe you didn't know this, so that if you roll 2 dice, you have a 50-50 chance of getting an even total or an odd total. Well, we can also think about things geometrically. So let's go back to our square of 64 different possibilities on the chessboard. All right, now I'm going to make a subset consisting of this fellow, this one, this one, this one, this one, these two, and this one. All right, this one here represents set B. All right, so here, B is a subset of S, so it's an event. It's really just the event consisting of choosing one of those boxes out of the total. And the probability of this particular event is, well, there's 1, 2, 3, 4, 5, 6, 7, 8 out of the 64 for a total of 1/8. All right, so that's what an event is. And now we can combine different events. So we can look at combinations of events. And we're in a probability space, SP. So if E is an event, then we can define EC, the complementary event. It's a set of S in S such that S does not belong to E. So this is the complementary event to the event E. And clearly the probability of this complementary event is just 1 minus the probability of E, because we're just summing up all the other probabilities, and all the probabilities add up to 1. Another important thing to be able to do is to take unions. So if A and B are events, then A intersect B is the event A and B, while we write A union B to represent the event A or B. Just mimicking the standard set theory notions. And then we can deduce that the probability of A union B is the probability of A plus the probability of B minus the probability of A intersect B. That's just inclusion, exclusion applied to the two subsets A and B. And if we have a partition, if, say, E1, E2, up to En is a partition of S, then the probability of E1 plus the probability of E2, and so on up to the probability of En, of course, has to add up to 1. All right, so that's all good. Notion of probability space, the idea of events inside them, the idea of a probability of an event. And now we want to get at something a little bit more subtle, the idea of independent events and the idea of conditional probabilities. So let's talk about independent events first. All right, so informally, A and B are independent events if knowing one gives no information about the other. Maybe I should say about the likelihood of the other, or the probability of the other. So the official definition is this. If A and B in S, P, are two events inside a sample space S with a probability measure P, then we say that they are independent precisely when the probability of A and B equals the probability of A times the probability of B. So there are lots of examples of independent events in real life. There's also lots of examples where the independence of events isn't entirely clear. So, for example, let's say I'm interested in the suppose the S is the set of all students. Okay, and suppose that I'm interested in those students who take math. Say A equals math students. And suppose I'm also interested in the set B. Might be the set of students who have a sister. And let's say we have another set, C, the students that like physics. Okay, so these are three different types of students in the general population. Okay, so I might be interested in these three different aspects of students, and I might be interested in independence. So independence would mean what? So I might be interested, for example, if the property of being a math student is independent of having a sister. So if I go around to all the students of the university and I ask how many of them have a sister, so some portion of them have a sister. Maybe with the probability 0.6 they have a sister. So let's say 60% of all students in the university have a sister. If it's also true that 60% of, or roughly 60% of math students have a sister, then those two things are independent. And my guess is that they would be largely independent. Being good at maths or having a likelihood for mathematics or an interest in it probably is independent of whether you have a sister or not. But I could be wrong. I mean, there might be some subtle link between those two things, but probably they're not connected in a long way. But how about this third condition, students that like physics? If I go around and poll people, do you like physics? Do you like physics? And I find out who likes physics. My guess is that if I know something about whether you like physics or not, I have a little bit more information than otherwise as to whether you're likely to be taking maths. Those two events are probably not independent. They're probably connected in some way. All right? So my guess is that A and B are independent, while A and C are not independent. And what independent means is exactly this thing here, this formula. Let's look at things diagrammatically where it's perhaps a little bit easier. So let's have a look over here, and we'll look at this example that we've already looked at. So here I have this set B. Let me introduce a few other sets. All right, so let's draw a line. Let's draw a line here and call everything here the set A1. And then in the next row, this is the set A2. The next row is the set A3. And everything below it is the set A4. All right, so we have these sets A1, A2, A3, A4. A1 is the top two, A2 the next one, A3, and then A4. And I have this set B, which I've denoted with these stars, crosses. Okay, so let's observe some things about these different sets. So first of all, we've already noted that the probability of B is 1/8. We can quickly calculate the probabilities of these various A's. So the probability of A1, well, it's obviously a quarter of the whole thing, so that's 1/4. The probability of A2, that's 1/8. That's the same as the probability of A3. And the probability of A4 is 1/2. All right, now let's have a look at B intersect A1. So B intersect A1, there's only one element in that set. There it is right there. That's the set B intersect A1. What's its probability? Well, the probability of B intersect A1 is 1/64. What about the probability of B times the probability of A1? The probability of B, we said, was 1/8. The probability of A1, we said, is 1/4. These things total up to 1/32. That's not equal to this, so these things are not equal. Therefore, B and A1 are not independent. If I know that you're in A1, that's telling me something about whether you're more or less likely to be in B. If I know that you're in A1, I know that your chance of being in B is reduced. It's reduced from 1/8 to 1/16. How about the probability of B intersect A2? Well, B intersect A2, there is A2 right there, that one strip, and there's only one in that set. So that probability is also 1/64. On the other hand, if we look at the probability of B times the probability of A2, the probability of B is still 1/8. The probability of A2 is now also 1/8. Now I get 1/64 for that as well. These are now equal. That means that, therefore, B and A2 are independent events. And what does it mean intuitively? It means that if I tell you that I'm in A2, and I ask you, what's the probability that I'm in B? The probability is just the same as it is in the big set. It's still just 1/8. You haven't learned anything about B if I tell you that I'm in A2. It's neither more nor less likely than it is in the big space. All right, so I'll let you check that, in addition, B and A3 are not independent. but B and A4 are independent. All right, I'll just mention a little proposition that if A and B are independent events from a probability space SP, then first of all, A and the complement B complement are independent. As are A complement and B. And second, also the complements of both of them are independent. A complement and B complement are also independent. All right, so let me indicate a proof for the first fact. So suppose A and B are independent. That means that the probability of A intersect B is the probability of A times the probability of B. That's what it means to be independent. Okay, but A equals A intersect B union A intersect B complement so here's our diagram, here's our big set, here is A, here is B. What I'm saying is that A is the union of A intersect B with A intersect the complement. There's A intersect the complement. Those things add up to A, and this is a disjoint union. There's obviously no things which are in both of those. Okay, so that tells us, therefore, that the probability of A is the probability of the first one, A intersect B, plus the probability of A intersect B complement. And so the probability of A intersect B complement is the probability of A minus the probability of A intersect B. And that is the probability of A minus the probability of A times the probability of B, because they're independent. And then that is equal to the probability of A times 1 minus the probability of B, which is the probability of A times the probability of B complement. And so therefore, A and B complement are independent, because the probability of their intersection equals the product of their respective probabilities. All right, so now we can talk about conditional probabilities. All right, this is a topic that's sometimes fraught with difficulties for students because there's some rather curious aspects of conditional probabilities and indeed some controversial aspects of the subject too. Okay, so if the main definition, if A and B are events from a probability space, say SP, then the conditional probability of A given B, that's the mouthful, the conditional probability of A given B is, first of all, the notation, it's including both A and B, so the A is first and then there's a line and then there's the B. So this is read as the conditional probability of A given B. And by definition, this is the probability of A intersect B divided by the probability of B. So this is the probability of A if you know already that you're in B. Okay, so you're no longer in the big set. The big set is S. Inside it there's this subset B, and we're interested in what is the probability of being in A if you know that you are in B. This is the probability of being in A if you know you are in B. All right, let's go back up to that example with the 64. And where were our x's? And I think we had A1 along here, and then A2, and then the thin one A3, and everything below it A4. And the x's were B. The whole thing is S. All right, so let's calculate a few probabilities. What's the probability of A1 given B? Well, first of all, let's use the formula. Okay, so the formula is that it's the probability of A1 intersect B divided by the probability of B. All right, so where is A1 intersect B? It is right there. There's A1 intersect B. That's a single guy. So its overall probability, the probability of that particular element, is 1/64th. And the denominator is the probability of all of B. That's 1/8. So we get 1/64th divided by 1/8. That is 1/8. On the other hand, the way you could look at it is to say, all right, it's the probability of A1 knowing that we're in B. So in other words, we restrict ourselves just to being in B. Forget about everything else. Sort of like making a smaller sample space just of B and asking, what's the probability that if we're going to choose something in B, that we end up choosing something in A1? Well, of the 8 possibilities, there's only one that will result in being in A1, and so it's 1 out of 8. All right, let's just write down a few others. So the probability of A2 given B, that's also 1/8. The probability of A3 given B is now there's 2 of them here. 2 out of 8 is 1/4. And the probability of A4 given B is, if you know you're in B, what's the probability in being in A4, which is this top, bottom half? It's just a 50-50 chance. 1/2. But we can also look at this same diagram the other way around. So also, the probability of B given A1. That's a different probability. That's now asking, all right, suppose that you know that you're in A1, what's the probability of being in B? From the diagram, there's A1. 1 out of the 16 possibilities is in B. So the probability is 1/16. But it's also, in terms of the formula, the probability of B intersect A1 divided by the probability of A1. The probability of B intersect A1 is 1/64th, while the probability of A1 is 1/4. And so we get 1/16th. And I'll just list the other ones. You can check them. The probability of B given A2 is 1/8. The probability of B given A3 is 1/4. And the probability of B given A4 is 1/8. Notice that these 4 probabilities that I calculated over here, they add up to 1. But these 4 probabilities don't add up to 1. Okay? So note, these don't add up to 1. All right, so in the next lecture, we're going to go further with conditional probability and talk about Bayes' rule. And there's interesting applications to medical statistics and other things of this rather unintuitive rule sometimes. So we'll see you then.